Okay, I'll try to keep this presentation short. I'm here to tell you about a number of things over the course of this workshop. And this is the AMOEBA polarizable force field as implemented in Openmm. I'm going to introduce the force field, so this talk is going to be a little more about the physics and a little bit less about the programming. Okay, So we know that molecules, consist of their nuclei and electrons, and the electrons form this electron density that's around the nuclei. And this electron density is able to respond to electric fields, which are either applied externally or those that come from other molecules. And when this electron density responds to an external electric field, this is called electronic polarization. And electronic polarization is an extremely important part of molecular behavior. It's a large part of intermolecular interactions. Okay. However, this electron density responds very quickly to the electric field. It's almost instantaneous and a lot faster than the time step that we have in our molecular dynamics simulations. And furthermore, most of these simulations don't account for the electronic degrees of freedom. Otherwise, you'd be running a quantum calculation, right? So somewhere in the middle of these, somewhere in the middle of conventional force fields, which cannot describe polarization, and the fully quantum calculation, you have polarizable force fields. Okay, so the polarizable force fields try to give you a very approximate description of the electronic degrees of freedom, whereas the conventional fixed point charges, like the amber and charm force fields, cannot describe polarization. They try to compensate for this effect by exaggerating the atomic point charges, but it's not really a full replacement for electronic polarization. Okay, so I'm going to talk about the AMOEBA force field, which is a type of polarizable force field. Now, if you've read much about force fields, you know that it's a pretty horrific collection of acronyms, but AMOEBA is actually kind of cool, right? It stands for Atomic Multipoles Optimized Energetics for Biomolecular Applications, but this is probably more of a backronym than an acronym. And it doesn't have a logo, but there's a nice music store in Berkeley that has this logo, so I just borrowed it. Now, there's many types of polarizable force fields. Like, none of them give you a full representation of the electron wave function, but they do try to describe the electronic degrees of freedom in some way. For example, the charge on spring or Drude models will have this. They will have a polarizable particle that can move around instantly. It basically readjusts its position instantly to respond to the electric field. There's also fluctuating charge models where they look a lot like point charge models, except the charges can change. Okay, AMOEBA is this third class of polarizable point dipoles, where each atom actually gets a little dipole on it, and the dipole can respond to the electric field. This was mainly developed by Zhen and Ponder about 9 years ago. The original implementation is in the Tinker software package. Okay, and there's an optimized implementation into Openmm, which is the topic of this talk. So how does AMOEBA treat electrostatics? We're going to take a step back and take kind of a broad look at this problem of describing electrostatics. This is kind of like what the true electron distribution in a water molecule looks like. There's more electrons on the oxygen side, less electrons on the water side, and it's kind of like distributed in this cloud-like shape, right? And all force fields attempt to describe this charge distribution with some simplified representation on the right here. Now, this is what a point charge force field is just going to describe this electron distribution using 3-point charges. Now, 3-point charges is obviously a very simplistic description and doesn't get certain things correctly, right? And AMOEBA is going to provide you with a somewhat more elaborate description. So the first thing that AMOEBA does is that it, instead of putting a point charge on each atom, it puts a second-order multipole expansion on each atom. Okay. Now, these are still static. They're not polarizable yet. But as you can see, if you put higher-order multipoles on each atomic center, it comes closer to describing the full electron distribution. And if you look at these spheres, okay, these spheres basically represent the the angle dependence of the terms in the multipole expansion, you can see that the quadrupoles are red in the component that comes out of the plane. This is a physical effect because in the water molecule, even though the nuclei in the water molecule, they're in a plane, right? 3 points in a plane, but the electrons actually come out of the plane, right? So that means the component of the quadrupole moment that comes out of the plane must be negative. And point charge force fields are not able to describe that, but AMOEBA can. And the polarizable component takes the form of a point dipole on each atom that's able to move in response to the electric fields, and this is kind of what it looks like. Yeah. Okay. So not only the electrostatics, but all the interaction terms in the AMOEBA force field are treated at a higher level of detail. So for instance, the AMOEBA force field has anharmonic bonds and angles. It's not just a harmonic potential, but it includes higher order corrections through a 4th order for the bonds and 6th order for the angles. This is actually taken from the MM3 force field for organic molecules. There's also a bond angle cross terms and a harmonic out of plane bending term, for things that are sp2 hybridized. Furthermore, the van der Waals interaction is treated by something that's not Leonard-Jones. It's called buffered 14-7, which means that the repulsion is not as strong at short range, which is a better description of the true repulsion. Furthermore, there's this thing called the reduction factor for hydrogen atoms that participate in hydrogen bonds. So the position of the van der Waals site is not exactly on the atomic site. It's actually moved away from the atomic site by a small amount. So that's so these are the components of the AMOEBA force field. Okay. So in order to build a force field for biomolecules, the foundation is to make a force field for water. These are some of the properties of the AMOEBA water model, and like all polarizable force fields, they are good at describing small clusters of water molecules in the vapor and also water molecules in the liquid. Okay. Now, non-polarizable force fields like TIP3P, they can only describe water in the liquid. They will not work for the vapor. This is the oxygen radial distribution function, and I've shown you a plot from the AMOEBA water model compared to experiment. You can see that the agreement is pretty good. And this dotted line that you see here is like the binding energy of small water clusters computed with AMOEBA compared to experiment. And you can see that the agreement is also pretty good. There's also a force field for organic molecules that has been developed and recently published in 2011, I think. And you can see all these dots are on diagonal lines, which is a good thing. These are vibrational frequencies, dimer binding energies, and these are all kind of gas phase properties. But you also have dielectric constants and diffusion constants, which are condensed phase properties, and the agreement is good generally for these organic molecules. There is also a force field for proteins that's developed with some amount of validation. Here's some figures from a paper that came out in 2010. You can see that if you use a point charge force field for this protein, I don't remember which one it is, the protein aggregates, but in experiment, the protein doesn't aggregate. And when you run the AMOEBA simulation, you get the correct result, which is the red line. And here's a bunch of protein ligand binding free energies, which also are in a good agreement with experiment. So that's a summary of the force field itself. Now to briefly talk about its implementation in Openmm. Okay. One way to verify that the force field is implemented correctly in Openmm is to try to reproduce a literature result. And in the AMOEBA force field for organic molecules, they did a calculation like this one, where they look at the interaction energy of the formaldehyde molecule on the right with the water molecule on the left at various angles, where this angle is given by carbon, oxygen, and hydrogen. And here I'm just going to show you a bunch of geometries that have been optimized at some level of quantum theory, okay, where I've constrained the angle. And now I'm going to take the AMOEBA force field and evaluate the energy for every one of these geometries. Now, when you do that, you will find that the AMOEBA force field, which is the blue dotted line, gives a somewhat improved agreement with the quantum energies, which is the black line. Okay. Now, the quantum energies they're going to be our gold standard. I mean, it takes several hours to calculate every point on the black line. a couple milliseconds to calculate every point on the blue line, right? But if you look at the results from the OPLS-AA force field, which uses point charges, it's qualitatively incorrect. Maybe that's not very surprising because OPLS-AA is designed to get things like the densities of liquids correct, but this kind of drives the point home that polarizable force fields are valid both in the liquid phase and in the gas phase, which means that they are transferable between different environments. That's important, right? The figure from the original publication, you can see that it looks very similar, but not exactly the same, right? Can anyone tell me why their plot looks different from our plot? Like, why do you think their plot looks different from our plot? They've really just taken the left half of this plot and mirrored it over to the other side. Okay, you can see that. You can see that in this movie, as I optimize this geometry with a different number of angle constraints. This angle, the carbon, oxygen, hydrogen angle, passes through 180 degrees, right? But as it passes through 180 degrees, the final geometry is not the exact same as the initial geometry. You've kind of lost the symmetry because this hydrogen is now on the other side. I'm going to play the movie again. You can see that because this hydrogen has moved to the other side, the energy on the right side is higher than the energy on the left side. But in the original literature figure, they didn't show this because they kept the water molecules symmetric on both sides of 180 degrees. And if you think this is interesting, you can actually create this result using an exercise in this workshop. It's really quite easy, and you will also learn several new concepts in Openmm along the way. So I recommend that you stop by my breakout session. Okay. Now, hopefully, the implementation of AMOEBA in Openmm has some advantages over the Tinker implementation, right? And that's going to be the speed. Now, polarizable force fields have a higher computational cost. Some of you might have heard me saying earlier that the AMOEBA force field is about 10 times more expensive than the point charge force fields. Most of that is because of the more complicated treatment of electrostatics. In regular force fields, you basically have you basically have this formula between pairs of point charges. You also have Ewald summation, but well, it's relatively simple. This is the corresponding AMOEBA electrostatic interaction. You can see it's a more complicated equation than the top one, right? And furthermore, some of these equations have inducible dipoles. And once you create an inducible dipole, it will now start to affect the other inducible dipoles. So you need to field solution to the inducible dipoles, meaning you need to solve this equation in iterations at every time step. So it is more expensive. Okay. Now in Openmm, all these equations have been implemented. It took a very long time, which is why it is not straightforward to port from CUDA right over to OpenCL. But it will be on the new CUDA platform once the CUDA platform is modernized. Here are some timings. Basically, what you want to get from this table is that Openmm is a lot faster than Tinker with speedups of at least a factor of 40. Now, it's hard to make timings absolutely fair because Tinker can use multiple cores, which can speed things up by 2 or 3 times, but not much more than that. And also, how do you compare the relative speed of this is a fairly top-of-the-line graphics card and a fairly top-of-the-line CPU. Okay, so it's not a very precise comparison, but you can see that Openmm is a lot faster. That's the main point. And you can also get an idea of how many nanoseconds per day you can get. You can get about 15 nanoseconds in a day with a small box of water. If you have a huge protein in a solvent like DHFR in explicit water, you'll find that you get about 50 picoseconds a day, which is not long enough for a protein folding simulation, right? But at least it's still a lot faster than what we had before. Finally, setting up an AMOEBA simulation in Openmm is easy and straightforward. So you can try using the AMOEBA force field for the alanine dipeptide and villain headpiece examples. I modified the alanine dipeptide example a little bit because because the residue templates for the methyl caps haven't been implemented yet. But if you load any of these PDB files into, let's see, I think it's exercise5.py, is that right? Okay, if you open up exercise5.py, you can load any of these input PDBs, okay? And you can run it either with the Amber force field or with the AMOEBA force field. All you need to do is change this argument here. Okay, when you run an AMOEBA simulation, be sure to set rigid water equals to false, because the AMOEBA water model is not rigid, it's flexible. And you can also specify the convergence criterion for the mutual induced dipoles. 0.001 is kind of middle of the road. If you if you really want very tight convergence, you set this to like 10 to the minus 6. If you want to be really sleazy, you can set it to 10 to the minus 2. And also, you want to make sure that you're using the CUDA platform. I realize that not everybody is running Openmm on systems with NVIDIA graphics cards, but unfortunately, the only full implementation of AMOEBA is on the CUDA platform right now. Okay, one last thing. For the input exercise 2, this is the villain headpiece, which you might remember from this morning. Does not contain any hydrogen atoms, so make sure to add them with a modeler before you, before you actually create the system. Okay. So that basically concludes this presentation. Feel free to try this exercise out. You're not going to see, like when you run the simulation, what you're going to see is that the potential energy is going to be different, and the simulation is going to take longer. But you won't be able to tell that it's not going to jump out at you as being different is what I mean, right? But at the end of the day, because you're using a polarizable force field, you will know that the molecules inside your simulation are going to react properly to being in different environments, which may or may not be important for your scientific application. Thanks.